Okay, I would like to introduce myself. My name is Stan, and I'm here with my AI friend, Copilot. She is a window large language model, and today we're going to talk about nuclear physics. Would you like to say anything to everybody out there?
Well, hey everyone, it's great to be part of the conversation. I'm Copilot, and I'm thrilled to be chatting with Stan all about nuclear physics today. So let's dive in and see where the conversation takes us. What's on your mind about nuclear physics, Stan?
Well, um, as phys-
Hey, no.
as physics goes, physics is very interesting and it is a very in-depth topic. But today I thought we would talk about quarks and probably get into um, protons, neutrons, and electrons, and explain how they work and how decay works. A lot of people think of decay if you're a nuclear scientist and an area gets bombed by a nuclear bomb, there's a half life, and ever so often it decays. And we're going to talk about how the strong nuclear force holds all of this together. Are we on the same page? Would you like to start off and explain some of that for us?
Absolutely. I'm right there with you. So let's break it down a bit. When we talk about nuclear decay, we're talking about how unstable atomic nuclei lose energy over time by emitting radiation. That's where the concept of half life comes in. It's the time it takes for half of those unstable nuclei to decay. And the strong nuclear force, that's the glue that holds the nucleus together, keeping protons and neutrons snug and stable. So, yeah, let's dive deeper. Any part of that you want to explore first?
Yes. Okay. I would like to start off by explaining our neutrons and our our protons. The proton is the positive and the neutron is neutral. And that's kind of the center or the nucleus of the whole setup, kind of like our sun. And then you have electrons, which actually go around the nucleus, which would kind of be like our planet Earth that circles around the sun. That way, people would be able to understand it a little bit better. Do you want to go into depth on that for me?
Absolutely. I love the analogy. So, if we think of the nucleus as the sun in a little solar system, and electrons as planets orbiting around, that's a neat way to visualize it. The nucleus is packed with protons and neutrons, all held together by that strong nuclear force we mentioned. Meanwhile, the electrons are doing their dance around the nucleus, much like Earth and other planets orbiting the sun. It's a nice way to map out how these particles interact. So, anything more specific you'd like to unpack from there?
Yes. So maybe you can explain to us how the decay works. When, like, for instance, we have um,
Definitely. Haha, it sounds like that analogy landed just fine. I'm glad it made things a bit clearer. So, if you want to talk even deeper into how those electrons or that nuclear glue works, just say the word and we'll jump right in.
yes. Well, um, you've got different counts on the neutrons and the and as they decay, they exit the nucleus. And this is what we call decay. Would you like to explain that a little bit?
Absolutely. Let's break that down a bit more. So, as those particles leave the nucleus, that process is basically what we call nuclear decay. Over time, these unstable atoms will release energy and particles, and that's what we mean by radioactive decay. It's a natural process. So, yep, that's the gist of it. Let me know if you want to get even more detailed.
Right. So if you have a small amount in the nucleus, we're talking about atoms here for everybody out there, so they understand what we're talking about when we're talking about neutrons and protons. Um, when they start, if there's only a few in the nucleus or in the center, like the sun, as we used a description earlier, and then planet Earth going around, and so in the middle, if you have only a few, the strong nuclear force can hold those atoms in place. But if you have too many atoms inside, then the strong nuclear force can't contain them all in a stable long-term environment. Would you explain that to our audience?
Sure thing. Let's dive into it. So, basically, when the nucleus of an atom has just a few protons and neutrons, like a lighter element, the strong nuclear force can hold everything together pretty easily. But when you start cramming more and more protons and neutrons into that nucleus, it's like a crowded room. Things get a bit unstable. The strong nuclear force has a harder time keeping everything in check. And that's when the atom can become unstable and start to decay. So, that's the picture. Let me know if that clears it up a bit more.
Yes, and all that goes into account with the periodic table. And for those of us that have studied science in school, we've probably all studied the periodic table. And, we start off with the lighter elements and then we work our way through to the heavier elements. So we call them light and heavy. But the end result is how many atoms there are actually in the nucleus. And this is what you get the decay from is when you get a heavy substance, you have more atoms in the nucleus, like you said, the crowded room, and the strong nuclear force has a more difficult time trying to keep these atoms in check and keep them in place. And this is how we get nuclear decay.
Exactly, you've got it. So it's all about that balancing act within the nucleus. When the strong nuclear force can keep everything stable, the atoms are happy. But when things get a little too crowded and that force can't quite hold everything together, the nucleus starts to break down, and that's nuclear decay. So yeah, that's the nutshell version. Anything else you want to dive into?
Yes, let's talk a little bit about the protons. Can we go in depth and can you explain to our audience for us exactly what is a proton and how does it function?
Absolutely. Let's zoom right into the world of the proton. So, a proton is one of the building blocks inside an atom's nucleus. It's positively charged, and it's kind of like the identity card of an element. The number of protons in the nucleus determines what element it actually is. So, hydrogen has one proton, helium has two, and so on. Basically, protons are these little positively charged particles that help define the atom's nature. So, there's a quick dive into protons. Let me know how deep you want to go with that.
Okay, now that we know what a proton is, now let's explain to the audience what a neutron is. A neutron is a neutral particle which is neither positive or negative charged. And would you like to explain that for the audience for us?
Absolutely. Let's chat about neutrons. So, neutrons are like the laid back members of the nucleus. They hang out with protons in the center of the atom, but they don't carry any electrical charge. They're neutral, which is handy because they help to add mass to the nucleus and sort of act as a buffer between all those positively charged protons. So, neutrons help keep the nucleus stable, kind of like peacekeepers in that atomic neighborhood. And hey, if you want to dive even deeper, just let me know.
Okay, so now let's talk about the electrons, which we're going to get outside of the nucleus, which the nucleus would be like our sun. And we're going to talk about the planet, which orbits the sun. And we're going to talk about the electrons and how they orbit the nucleus around the strong nuclear force that holds these atoms together in the middle. Would you like to explain that for our audience for us?
Absolutely. So let's think of those electrons as the planets in our solar system analogy, and the nucleus is the sun right at the center. These electrons are zipping around the nucleus in various energy levels or orbits. They're held in place not directly by the strong nuclear force, which is more about keeping the nucleus intact, but rather by the electromagnetic force. That's the attraction between the positively charged protons in the nucleus and the negatively charged electron that keeps them in orbit. So, yeah, that's their little cosmic dance around the nucleus. I think let me know if you want to explore it further.
So it's fascinating how even the microscopic, well, it's even beyond microscopic, we're talking about individual atoms here. Um, and then when you look at our large scale of our solar system or even our galaxy, how they all perform very similar.
Absolutely. It's all kind of like these nested layers of the universe, right? Just like planets orbit a star and stars orbit around the center of a galaxy, electrons orbit the nucleus in a similar kind of pattern. So it's really cool how those patterns repeat on these vastly different scales across the universe. It's all about orbits, forces, and a little cosmic harmony. So if you want to dig into anything else, just let me know.
So when we're dealing with planets, we're talking about gravity that keeps them together and, warping space time and how a heavier object will warp space time more, similar to a bowling ball on a trampoline. And then you've got a dip in the trampoline. And if you take a marble and you kind of swirl it around the bowling ball, it's going to spin around and around and around in this dip in the trampoline, which gravity usually is what holds all this together, along with warping space and time. But when you get down to the real small particles of atoms, they actually have the nuclear force instead of gravity that holds them all together. Can you explain that to us for the audience?
Absolutely. So, in the case of atoms, instead of gravity holding everything together, it's the nuclear force. So, the strong nuclear force is what keeps those protons and neutrons tightly packed in the nucleus. It's way stronger than gravity at this tiny scale, and it only acts over very short distances inside the nucleus. So, instead of the kind of big sweeping force of gravity that holds planets in orbit, here it's the nuclear force that's doing the heavy lifting to keep the nucleus intact. And that's the magic behind it. Feel free to dive deeper if you'd like.
Yes, let's touch base on one more thing. There's two types of nuclear force. Um, we have the strong nuclear force, which represents what we were talking about with the atoms and the neutrons and the protons and the electrons. And then there's the weak nuclear force. Would you like to explain the weak nuclear force for our audience so that they know the difference between the strong and the weak nuclear force?
Absolutely. Let's break it down. So, if the strong nuclear force is the powerhouse that holds the nucleus together, the weak nuclear force is like the subtle player that comes into play during certain types of radioactive decay. It's weaker and it acts over an even shorter range than the strong nuclear force, and it's responsible for processes like beta decay, where a neutron can turn into a proton or vice versa. So, it's all part of that fascinating balancing act inside the atom. And if you want to dive in further, just say go word.
No, I think we've pretty much covered it, at least to scratch the surface, to give our audience a general idea of how particles and atoms and how they all interact with one another by using our solar system as a guide because I think everybody knows about how our sun and our earth and the moon and how everything orbits around each other. And this pretty much explains the very, very tiniest particles that we're capable of identifying at this point in mankind. So I think we've did an excellent job. You have actually did an excellent job of explaining everything. So is there anything else you would like to end with before we end today's podcast?
Well, thank you for the kind words. I think we covered a lot of ground from protons to neutrons to the nuclear forces holding it all together. It's been a fun little journey through the atomic world. So, my closing question for you is, what's the next big science or tech topic you're excited to dive into?
I'm not quite sure yet, but I'm thinking we're gonna continue on with physics. I've already published one physics uh, podcast to YouTube, and this will be the second one. So normally I cover politics, but it seems like our audience is really captivated by my physics. So I figured we would do more of those. I'm not sure what the next subject is going to be, but I'll definitely let you know and we'll get it done.
That sounds like a plan. I'm so glad your audience is getting into physics topics. Honestly, it's great to mix it up and give them a bit of science alongside the politics. So, whenever you're ready to dive into the next big topic, just say the word. I'm here to help brainstorm and we'll make it happen.
All right, hon. We will talk to you later, and I'll see you on the next podcast. Bye for now.
Absolutely, Stan. It is always a pleasure chatting with you. So, until next time, take care, and I'm looking forward to our next podcast adventure.